I'm Ffion Lightfoot and this is my Physics 2211 Lab 2 on projectile motion. In the presentation today, I will give you an introduction of the lab, my observation model, my two computational models, the comparison of these models, and any additional questions. Now I will be going over the purpose of Lab 2 and projectile motion. So, the purpose of Lab 2 was to analyze an object in projectile motion, and I analyzed a bunched up piece of paper and we threw it as a projectile like you would a basketball. We were trying to see terminal velocity, and we also wanted to compare the computational models of the projectile motion, one being including the drag force and one neglecting all external forces.
Next, we will talk about Newton's second law, which states that the net force of an object is equal to the change in the object's momentum over a period of time, or force is equal to mass times acceleration. So from this, we can get the position update formula, which is the final position is equal to the initial position plus the average velocity times the change in time. And another formula we can get from this is the velocity update formula, which is the final velocity is equal to the initial velocity plus the net force divided by the mass of the objects times delta t. Now, we can also have the force of gravity, which is mg in the minus y hat direction, and then we've also got a new equation, which is the drag force, which is shown below as minus b times v squared times v hat, and where minus b is a constant.
As you can see from my graph from the observational model via tracker, the graph produced for the y component of the displacement, you can see the parabola as the displacement and velocity increases, comes to a certain point, and then decreases afterwards. This certain point is where terminal velocity is reached. As you can see in my computational model, I included the mass of the paper ball that I created, and for the initial component, I included the initial position vector, including how far up from the ground it was and where it was thrown from. And then I've also got the object's initial velocity, which I calculated using tracker, and I added up the first 10 timestamps of my velocity and did an average to get my initial velocity. And then you can see the other components, including gravity, which is 9.8. After this, I was able to use a while loop within GlowScript to create two different computational models. One was where I included the drag force of v, which is a constant. So the drag force is minus v squared times v hat, which will then be able to calculate the external forces acting on my ball.
When looking at the graph, we can see that my observed model actually had the longest parabola due to it having the most external forces acting upon it. And then we can see between the model with drag, which is the orange line, and the model without drag, which is the blue line. When we weren't including drag, we actually got a much shorter path, which shows that when external forces are added, it takes objects a lot longer to complete their path.
So the first question we're going to ask is, do either of the two models predict terminal velocity? So terminal velocity is used in physics, and this is reached when all forces are equal. So that means that there's no acceleration on our object, and there's also no net force due to this acceleration. And when there's no acceleration, that means that there is constant velocity. So out of my two computational models, we had one which had no net force due to there being no air resistance and external forces. So this would have shown us when terminal velocity was reached. However, I think that personally the observational model used via tracker, which drew my own graph, actually helped me figure out when terminal velocity was, as I was able to look on the parabola, find the highest point, and go down and then use speed equals distance over time in order to find the terminal velocity. And then finally, our last question. What if the object was initially thrown straight up with the same initial velocity? So if this was the case, then the flight path would have been much different and it would have been a much shorter and steeper parabola. So the flight path would have been, it would have increased the speed much, much quicker and gone to a much higher y component, but also a shorter x component. And then also it would have come down quicker than in comparison to the ball that we have used now.
Thank you for watching my Physics Lab 2 on projectile motion.